Today I'm going to show you how to do spectroscopy analysis in 4 steps by using a specific problem. So these are the 4 steps. So first we need to find out the molecular formula. So from our mass spectrum, we can spot the molecular ion peak here, which is 164. And this is an even number. So by nitrogen rule, it can tell us our formula has either 0 numbers of nitrogen or even numbers of nitrogen. And from the HNMR spectroscopy, we can add up all the numbers of hydrogen, which is 5 plus 1 plus 1 plus 3 plus 2. So the numbers of our hydrogen are 12, or it can be 12 multiplied by a positive integer. But the situation where n is an integer that is larger than 1, let's say n is 2, is highly unlikely because that requires the structure to have a high degree of symmetry. So let's just say it's 12 for now. And we check out the carbon NMR and we count how many peaks are there. So there's 1, 2, 3, 4, 5, 6, 7. And it gives us the numbers of our carbon is going to be equal or larger than 7. And from this peak at about 180, this implies that we have a carbonyl group. And this region is the double bound or aromatic region. From the HNMR spectroscopy at about 6.9 ppm, there's 5 hydrogen, which tell us we have a non-distributed aromatic ring, C6H5. But in the carbon NMR, in this aromatic region, there's only 4 lines. So we've actually missed 2 carbon because it was supposed to be at least 6 carbon atoms in this region. So our numbers of carbon is going to be equal or larger than 7 plus 2, which is 9. And from the IR spectrum, you can see at 1678, there's a very strong peak, and it indicates we have a carbonyl group. So the numbers of our oxygen is going to be equal or larger than 1. And we can add up these formula we've gathered right now, and it adds up to C9H12O. And we already know that the molecule mass is 164. So 164 minus the mass of C9H12O gives us 28. And 28 can be composed of 2 nitrogen or 1 carbon and 1 oxygen. So let's see which is the case. If it's going to be 1 carbon and 1 oxygen, that means we have no nitrogen in this formula. But we can see from the HNMR that there's in total 4 hydrogen that can have hydrogen exchange. it means that these hydrogens are active hydrogen. Active hydrogen are usually from hydroxyl group or amine group, or hydrogen that is attached to a sulfur atom. So if we don't have any nitrogen in our formula, we're gonna cancel this possibility, and we're gonna cancel this one too because we don't have a sulfur atom. And that means we're going to have 4 hydroxyl group because there's 4 active hydrogens, but that is not gonna happen. If we have 4 hydroxyl group, that means we'll have 4 oxygen atom, and the molecular mass is going to be more than 164. So it can only be the case that we have 2 nitrogen atoms. So now we have the formula, which is C9H12N2O. So we can move to the next step, which is to calculate degree of unsaturation. And to calculate this, you just follow this equation, which is going to be so our degrees of unsaturation is 5. And it's going to be because of the aromatic ring plus a carbonyl group. And then we move to the next step, which is find out a structural unit. So the most useful tool you can use when finding out a structural unit is by HNMR spectroscopy. So let's take a look at this graph. So at about 1.1 ppm, there's 2 hydrogen, and it looks like a single peak. And they're active hydrogen, so it's going to be an amine group. And at about 2.1, 2.5, 2.9 ppm, there's 3 hydrogen. So you might want to think it is because we have 3 methylene group. But if we have 3 methylene group, they need to have extra groups that are attached to them, right? So it's going to be a little hard, and we're going to just set it aside first and look at the other hydrogen groups. So this one we already know are the aromatic ring, and these two are active hydrogen too, and because the oxygen are already used in a carbonyl group, so we don't have any hydroxyl group. So they can only be because of another amine group. But normally, because these 2 hydrogens are attached to the same nitrogen atom, these 2 hydrogens are supposed to be equivalent. So they're not supposed to be separated in a graph. But now we can see 2 peaks of the 2 hydrogen, which means they are not equivalent. And that is likely to be caused by a chirocarbon, which means the amine group is attached to a chirocarbon, and the chirocarbon is causing the 2 hydrogen to separate. And now we add up the unit we currently know, and there's 2 amine group, an aromatic ring, a carbonyl group, and it adds up to C7H9N2O. And we already know our formula was C9H12N2O. So we find out there's a C2H3 left, which is contradictory to our hypotheses that we are gonna have 3 methylene group. And C2H3, because we don't have extra unsaturation point, can only be made up of 1 CH and 1 CH2, which means in this graph, the 2 hydrogen in the CH2 is splitting again. And the reason why it's splitting is just as the amine group. It is because of the chirocarbon. So that means the chirocarbon here, the chirocarbon is supposed to be this carbon. And it is connected with a amine group and a CH2. And we can confirm this by looking at the zoomed in graph, which we can see their coupling constant. So let's mark these hydrogen first. So let's say this is hydrogen A, this is hydrogen B, and B dot, because it is splitted on a graph, which means they are not equivalent. And this is hydrogen C. So for hydrogen A, is going to be coupled with hydrogen C and hydrogen B. And hydrogen B and C are not equivalent, so it's gonna roughly be, by the n+1 rule, split into 2 plus 1 multiplied by 2 plus 1. So it should be 9 peaks in total, but of course we're not gonna really see 9 peaks on a graph, because there's definitely gonna be peaks that are overlapped. So we're just gonna say it is a multiple peak. And if you look at this graph, you can see, I'm gonna say this one is hydrogen A, because the coupling constant are similar, because hydrogen B are 3 bonds away from hydrogen A, and hydrogen C are also 3 bonds away from hydrogen A. So the coupling constant are both J3, so they're similar. And for hydrogen B, it's going to be coupled with hydrogen A. So for hydrogen B, it's going to be coupled with hydrogen A and hydrogen B dot. So first, this is the initial signal of hydrogen B, and it's going to be split up by hydrogen A. And this is going to be the coupling constant. And since hydrogen B is 3 bonds away from hydrogen A, is going to be a J3. And then it's split by HB dot. And HB dot is only 2 bonds away from HB, because they're connected to the same carbon atom. So it's going to split up like this, and this distance is J2. So the peak is going to be something like this, and we call this a double peak. And you can see, so this one is going to be HB, and this one is going to be HB dot. So now we add up our structural unit and see if it matches with our formula. So we have 2 amine group and an aromatic ring and a carbonyl group and CH, CH2 and This carbon also has an amine group connected to it, but we've already counted the amine group at here, so we can't double count it. So it all adds up to C9H12N2O, which is exactly the same as our formula. So we've found out all the structure unit. So we go to the final step, which is we're going to connect our structural unit. So since we already know that our aromatic ring is monodistributed, that leaves us only two ways to connect the units. So we're going to call this structure 1 and call it structure 2, and we're going to see if we can find out which one is the correct one by looking at the mass spectrum. So from our mass spectrum, we can see three prominent peaks at 164, 120, and 91. So the mass to charge ratio at 120 is not going to be very helpful because both structure 1 and structure 2 can have this ion. And it is likely due to the I cleavage. So for structure 1, the bond is going to break at here. And we'll have this ion. And for structure 2, the bond is going to break at here. We're also going to have this peak. So what's really going to help us to find out the correct structure is going to be the peak at 91. So for structure 1, the peak at 91 is probably due to the rearrangement, the Lafferty rearrangement. So if we write our structure like this, this hydrogen is going to end up here, and the bond is going to break at here, and we're going to have this ion, and its mass to charge ratio is going to be 91. But for structure 2, we can count the carbon, and this one is alpha, beta, and gamma. So there's no hydrogen on the gamma carbon, so it's not going to have a rearrangement. But if we look at a carbonyl group and we count the carbon, so from here is alpha, beta, gamma, and there's no hydrogen on the gamma carbon, so it's not going to have a rearrangement. But if we count it like this one is alpha, this one is beta, and this one is gamma, it can have rearrangement, but it's not going to have a peak at 91. So by rearrangement, it's going to have an ion like this. So in this way, we can confirm that our structure is going to be structure 1. And this is the whole process of our spectroscopy analysis, and I hope this video is helpful to you, and please correct me if I said anything wrong.